Welcome to the deep dive. Today, we're going to be tackling LLMs, large language models, these AI systems that can write just about anything.
Yeah,
And you've given us a fascinating research paper
it is fascinating.
to unpack here. MONET, mixture of monosemantic experts for transformers.
Oh, it's a mouthful.
Yeah.
I know.
Yeah.
But the core idea is really, can we make these powerful LLMs more transparent?
Mm,
Imagine understanding exactly how an AI thinks,
right.
what parts of its structure are responsible for specific knowledge,
Yeah.
and how that knowledge could be accessed or even edited.
That's our mission today.
Yeah,
And it all starts with the problem the paper calls polysemanticity.
right.
What is that?
It's the idea that in current LLMs, the individual components, the neurons, can react to a huge range of unrelated things.
Okay.
One neuron might fire up for the word apple, a picture of a cat, and a line of Python code all at once.
Wow.
This makes it really hard to pinpoint what any given part of the model actually knows.
So it's like trying to decipher a language where every word has 100 different meanings depending on the context.
Exactly. And that's where MONET comes in.
Okay.
It proposes a new architecture for LLMs,
Okay.
one that tries to break down these complex models into more understandable,
Right.
specialized units.
So more specific.
Yeah, think of them as experts,
Okay.
each focused on a single specific type of knowledge.
Gotcha.
Yeah.
The paper's abstract talks about enhancing mechanistic interpretability
Right.
and being able to resect the internal knowledge. That sounds intense.
It is.
Okay.
Mechanistic interpretability means we're not just looking at what the LLM spits out as a result.
Okay.
We want to understand the actual mechanisms,
Yeah.
the step-by-step process
Ah.
of how it arrived at that output.
Like being able to follow the AI's train of thought rather than just seeing the final destination.
Precisely.
Cool.
And resecting knowledge means being able to pinpoint and manipulate specific pieces of knowledge within the model. What if we could isolate the part that understands chemistry,
Yeah.
for example, and edit or remove that knowledge entirely?
That's both incredible and a little unnerving.
Yeah.
But before we get ahead of ourselves,
Right.
how does MONET actually work?
Okay.
The paper starts by talking about existing methods like sparse autoencoders
Yeah.
or SAEs.
SAEs try to disentangle the features in LLMs,
Okay.
but they often hurt the model's performance.
Yeah.
It's like trying to understand a car engine by only looking at the exhaust fumes. You're missing the inner workings, the intricate connections between the parts.
So are we stuck in a trade-off?
Right.
If we want to make LLMs more understandable, do we have to sacrifice their abilities?
That's the challenge MONET aims to solve.
Okay.
It tries to achieve both interpretability and more performance by changing how the LLM is trained from the ground up.
Mm.
To do this, they use an approach called mixture of experts, or MOE,
Okay.
architectures.
MOE, that sounds intriguing.
It is.
So what exactly is an MOE?
Think of it like having a team of specialists
Okay.
instead of one generalist.
Yeah.
Each expert in the model focuses on a specific type of knowledge,
Right.
and the model learns how to route inputs to the right experts.
Okay, I'm starting to see the connection to the monosemantic experts idea.
Yeah.
But the paper points out some limitations with typical MOE architectures.
Right.
What are those?
Most MOE models don't use enough experts to allow for real specialization.
Oh, okay.
Plus, the knowledge within those experts can be scattered throughout the model,
Yeah.
making it hard to access.
So MONET's solution is?
More experts.
More.
A lot more.
Okay.
Instead of hundreds or thousands, MONET scales up to 262,000 experts per layer.
Wow, that's a massive team of specialists.
It is.
But wouldn't that make the model incredibly complex and resource heavy?
That's where the ingenuity of MONET comes in. They use a technique called product key composition. Imagine each expert is like a specialist with a unique set of skills. Instead of having 262,000 completely separate specialists,
Right.
MONET breaks down those skills into smaller components that can be combined in different ways.
Ah, so it's like having a team of experts who can share their knowledge and skills to cover a wider range of areas?
Exactly. Figure 1 in the paper does a great job of visually illustrating this difference in scaling.
Okay.
It's this clever design that allows MONET to handle so many experts without requiring a supercomputer to run it.
So we've got this massive organized team of experts.
Yeah,
But the real test is,
Right.
can we actually see these monosemantic experts at work?
That's where it gets really exciting.
Okay.
Figure 2 of the paper shows actual examples of these experts in action.
Okay, I'm looking at figure 2 now.
Okay.
One example shows an expert that lights up when the model encounters chemical compounds, like chloric acid or SO2.
What's amazing is that we can now pinpoint the exact part of the model that seems to understand chemistry. This level of granularity opens up possibilities for understanding how the model represents knowledge.
Right.
And potentially even manipulating that knowledge.
There are other fascinating examples, too. Experts for states in the U.S., Bayesian statistics, even code in different programming languages.
Right.
Each expert seems neatly focused on its own little domain.
And that brings us back to our mission.
Okay.
We've seen how MONET breaks down knowledge into these specialized modules.
Right.
But can we actually do anything with this? Can we edit this knowledge?
Right.
Control it?
Yeah.
Make the model safer?
That's what we'll explore in the next part of our deep dive. Thanks. Welcome back to our deep dive into MONET.
Yeah.
We've laid the groundwork understanding how it breaks down complex LLMs into those fascinating monosemantic experts.
And now we get to the truly mind-bending stuff.
Yeah.
Can we actually manipulate this knowledge? The researchers put MONET through some rigorous testing.
Right.
And the results are pretty remarkable.
They call one of their experiments domain masking.
Yeah.
Is that like putting a blindfold on certain parts of the model?
It's a good analogy.
Okay.
They wanted to see if they could selectively remove knowledge in specific areas without affecting the model's performance elsewhere. To do this, they used a benchmark called MMLU, which stands for Massive Multitask Language Understanding.
So a real test of an LLM's broad knowledge across different subjects.
Exactly.
Yeah.
MMLU covers a wide range of knowledge domains.
I hear you.
From basic math to U.S. history to computer science.
It's a real variety.
Yeah. And they used a version called MMLU Pro, which breaks it down even further.
Okay.
Into 14 specific domains like biology, law, and engineering.
Looking at figure 3 in the paper, it shows the results of this domain masking. It seems like they were able to make MONET unlearn specific subjects, almost like surgically removing that knowledge.
That's a great way to put it.
Okay.
For example, they could mask out the experts responsible for chemistry, and the model's performance on chemistry-related tasks would drop drastically.
Right.
But its ability to answer questions about history or law remained completely intact.
So it's not just that the model is confused, it's like that specific knowledge is truly gone.
Precisely.
That's wild.
And when they compared MONET to other methods like sparse autoencoders, MONET consistently outperformed them in this targeted knowledge manipulation.
Okay.
The other approaches tended to cause broader performance issues, while MONET allowed for this very precise unlearning.
This is where it gets really exciting for me.
Yeah.
It seems like MONET opens up possibilities for controlling LLMs in ways we haven't been able to before.
And they didn't stop there.
Oh, really?
They also tested multilingual masking, using a version of MONET trained on code called CodeMonet.
So could they make CodeMonet forget how to code in a specific language, like Python?
That was the goal.
Okay.
And the results are in Table 3.
Yeah, I see that.
That's pretty solid.
What were the results?
Deleting the experts associated with Python caused a major drop in its ability to generate Python code. But the model could still write code in other languages like Java or C++ just fine.
It's almost like they gave the model selective amnesia.
Right.
This research feels like it's pushing the boundaries of what we thought was possible with LLMs.
It is.
Yeah.
Imagine being able to tailor an LLM for a specific task.
Right.
Equipping it with only the knowledge it needs, and removing anything irrelevant or potentially harmful.
That's huge.
The possibilities are vast.
Yeah.
And we'll dive into some of the potential applications in the next part of our deep dive.
Welcome back to the deep dive. We've been on quite a journey exploring MONET and its potential to revolutionize how we understand and control LLMs.
We've seen how it breaks down these complex AI systems into those specialized monosemantic experts.
Right.
And the remarkable level of control that provides.
We've even seen how researchers can actually edit specific knowledge within these models. It's mind-blowing stuff.
Yeah, it is.
Yeah.
And it raises some really interesting questions about the future of AI.
It does.
What could this level of control mean for how we use and interact with these increasingly powerful systems?
That's what I'm most curious about. The paper's conclusion hints at a future where we could create LLMs tailored for very specific tasks, domains, and maybe even ethical guidelines.
Imagine being able to design an AI that's not only incredibly capable, but also perfectly aligned with the task at hand.
Yeah.
It could have a huge impact on fields like education, scientific research, even creative writing.
It would be incredible to have LLMs that are powerful tools for problem solving, but also safe and reliable.
And potentially much more efficient as well.
Okay.
If we can tailor LLMs to specific tasks,
Right.
they might not need to be as massive and computationally demanding.
Right.
That could make them more accessible and sustainable.
That's a crucial point as these models continue to grow in size and complexity.
Yeah.
We need to find ways to make them more manageable.
But of course, with this level of control come new challenges.
Course.
There are important questions about who gets to decide which knowledge is included or excluded from these models.
It's almost like we're talking about shaping an AI's values and worldview.
Exactly.
That's a huge responsibility.
It is. And it's something that researchers and society as a whole will need to grapple with as this technology advances.
Yeah.
The paper's authors acknowledge these challenges and call for more research into the ethical implications of Monet and similar approaches.
It sounds like this is just the beginning of a whole new field of research
Oh, yeah.
around understanding and controlling these monosemantic experts.
Absolutely. There's so much more to explore.
Yeah.
For instance, the methods they use to identify and select experts were relatively basic.
Okay.
There's a lot of room for developing more sophisticated techniques.
This has been such an eye-opening deep dive.
Yeah, they have.
We've gone from the nitty-gritty of how MONET works to these big picture questions about the future of AI.
It really highlights how quickly this field is advancing and the incredible potential for both positive and potentially challenging implications.
So before we wrap up, let's leave our listener with something to ponder.
Oh?
Imagine a world where we can create custom-designed LLMs,
Yeah.
each tailored for a specific purpose. What possibilities does that open up? What challenges do we need to be prepared for?
These aren't easy questions, but they're questions worth asking as AI continues to reshape our world.
Thanks for joining us on this deep dive into the world of Monet.
My pleasure.
We hope you've enjoyed exploring the potential of these groundbreaking ideas, and who knows, maybe you'll be the one to make the next big breakthrough in AI. Until next time, keep exploring, keep questioning, and keep diving deep.